await on it while the thread did something else. So at this point, this became a time when, well, the performances became significantly faster, and you didn't have this typical forum website from 2000s that was lagging even if it reported 10 users. Nowadays, you have like modern web servers like Nginx that can answer like 80,000 requests per second per CPU, which is quite an upgrade. And these servers are generally called rather fast. And people often just complain about some Python frameworks, like this one is fast, it can do 30,000 requests per second and so on. Yeah.
Request from the Zoom, if you can turn on the camera.
Turn on the camera.
Yeah, I mean.
Okay, I guess I look good enough so that I can turn it on. Okay, can you see me now? Oh, yeah, well, there aren't enough seats. Yeah, somebody can take my chair because I'm not gonna sit. Oh, actually, yeah, there are so many chairs. Okay, so yeah, I told you it wasn't a good idea to start at 18:30.
People to come in and, you know, at the start, but not the start.
Here are extra chairs. Do I hear more footsteps? Nope. Okay, so I'll quickly summarize what I was telling before. Yes, you did your resume. Well, usually the newest ones, or like roughly the newest ones, not some kind of. Well, that is a problem, that you just find some information about some estimates and so on, and you realize that this estimate came out, but you see it written on Stack Overflow, you look how old it is, and you are not certain how well it works on newer CPUs. So this, well, I'm gonna throw these numbers. You should always assume that there will be a plus minus 20%, okay? Because there is no way to put this accurately, and I wasn't really just trying everything I ever mentioned to made a POC and tested how it works on the same CPU that I tested everything. But usually I try to stick to the newest CPUs. Okay, so to quickly, because 5 new people arrived since I started, so I'm gonna summarize it quickly. I'm gonna use, well, this will be mostly, well, this will address more issues, but this will be mostly about cases when you don't control the protocol, where you have done real, like if you have a situation like you have UDP, you have your own package, your own protocol, you do everything binary. This like usually just do the obvious things, and there will not be many parts of this talk that are actually relevant. This will mostly for the usual use cases. You don't control the protocol. There is some standard typical protocol, and you are still trying to be the fastest. And I'm using the web server as an example because there are so many different protocols for that. No, so many different protocols. Just all of the protocols are pretty much fixed. You just do REST API always. So, and pretty much everybody knows this. So I'm using web service as an example, but so I put a short story what was the story of a fast web server in the past, and how is it approaching, and how are people upgrading in the present just by rediscovering that they might actually use multi-threading instead of multiprocessing and so on. But let's say that currently a pretty standard way of handling this is to use Nginx, which is reportedly a relatively fast server. Or, well, they say it's quick server, probably because it's better than Apache. And it does maybe 80,000 requests per second per CPU, which, as I said, is not particularly accurate, but that shouldn't matter so much. Well, as I have quickly made some searches about things that if that's in most servers, typically you can cache some database calls, which will be usually the bottleneck. So people can get to pretty much like 20,000 requests per second if it actually needs to get access some mutable data, but it's still a cache, so there might be some temporary abnormalities. Of course, in practice, to optimize this, it will be spread to have like many CPU cores, maybe NUMA architecture. You may have actually spread it across multiple servers, but like the database, which like typically everybody, well, a lot of these projects use Postgres, which is again known for being relatively fast. And given that you communicate with it using assembly or chair. Given that, what was I talking about? Yeah, actually this, well, Postgres typically communicates via TCP. So you can easily just put it into another device so that you just don't have to run everything on the same device to just get more power. And this is easier to spread. But from a certain point, actually, these individual servers cannot just be strong enough, and you just start multiplying them, in which point it becomes a distributed system. And of course, nowadays we have this modern cloud architecture that allows new servers to be added seamlessly into the system and so on, which is, of course, always comes with a great advertisement and, of course, a great amount of margin earned by the cloud provider. So I was told you need to scale if you reach 1 million simultaneous users. Given the numbers I have shown before, she was right when she told that. However, we have to think about this. As Urban Dictionary said, the men who program C++ are real men. The women who program C++ are real men too. You can spot a C++ programmer from their testosterone-fueled swagger and the unbelievable amount of content they inject into the phrase Java programmer. They'll probably do the air quotes at all. Okay, so we are C++ programmers. And those are girls' wisdoms. We are the real men. So how about just making it faster using the tricks that we generally know? So first, we have unordered map. And if you look at these designs that these distributed systems frequently use, you see that they just frequently mention Redis, which is a key value database which is kept in memory. Okay, seems like that unordered map. Okay, so that's like one point that actually this can have pretty much significant influences on performance, especially if you think that they start speaking about NoSQL, which is basically just, again, key value databases where you just do a fancy unordered map. So next problem, which is actually very significant mutexes and atomics on hot path, we need to minimize these because, well, actually very often your server is fast, but everything just ends up bottlenecked at one place. Next thing is allocations, because you can just make things, well, typically if you are writing C++ code and you manage to figure out how to avoid allocations, your code will be faster and also actually typically much more resilient to memory problems. So sometimes if I just slowly adapted this kind of approach to avoid dynamic allocation just by design, I didn't see very frequently these errors that Rust is trying to solve. Next thing is SIMD-based string operations. I have found that this is really crazy when it comes to improving performance of parsing text-based protocols, which are everywhere. Next approach is that there are different approaches of parsing it, but typically if you just write a state machine, it's actually very annoying to write and also surprisingly fast. And there are also some other optimizations that I found are pretty useful and surprising. And one point that is particularly important is bypassing operating system sockets, which, well, you know, like Unix sockets, Windows sockets, and so on. So let's go one by one. So the idea of in-memory database. Well, if you can put stuff into .vector that you are just working hard with, yeah, it will of course be very fast. Another map has this problem that it requires iterator stability, which has a super disadvantage that you are forced to use a lot of small dynamic allocations to scatter, and you will have the whole thing scattered across the memory, which means your memory locality will be miserable. And this is all just the consequence of the one requirement that if you add a new element, you will not invalidate iterators. That means if a rehash occurs, the elements cannot be moved to different locations in memory. This is addressed by a lot of custom containers, and Boost Unordered Flat Map is, well, one that is super easily available and is quite well rounded. There are some other types you can find that will be better for specific purposes, but I have found this one like good to go for this example. And also almost all use cases unordered map, you just find and replace with Boost unordered flat map, and it will just work. So the speeds of these container operations, assuming we are at around roughly 1 million elements, so that we are not just working on a small container, we actually have a lot of data there. So inserting elements into vector, 120 million operations per second. This is actually the slower type. Insert element into unordered flat map, 30,000 operations per second. Wait, sorry, I explained it wrong with .vector. The problem is that there are some custom vectors that optimize insertion in some ways, because reportedly .vector is not particularly efficient for insertion. But of course, if you are just looking up an element, this is an array access, so there is no way for it to be faster.
Insert element in vector.
No, I mean at the end. Of course, if you are just adding it into middle, it will be inefficient. That's but well, usually that's the use case you want to avoid with .vector. If you are removing one element from the vector, you can optimize it by swapping the element with the last element and deleting the last element. Then modify element in vector. I was able to get to 300 million operations per second. Modifying element in unordered flat map, 50,000 million operations per second. Now remember the part where they were using cached queries to Postgres SQL database that had 20,000 operations per second. the point is, you may use the database for saving your data or like persisting it over instances, but seriously, if you just keep the stuff in typical C++ containers, you just the difference is massive. I was also making other benchmarks out of curiosity, like if you just dynamically dynamically allocate an element like a string of any size. I put it into an unordered flat map, and I get around 30 million operations. If if it is statically allocated but string indexed, so that you actually need to compute some kind of hash in some like quick way, you still get to 40,000 operations, 40 million operations per second, which is quite a difference. Given that you are avoiding one indirect access, like to a wild place randomly in memory. Actually, yeah, I'm comparing pears to apples here because I was curious about this specific case or something. Yeah, this isn't a good comparison, but I'm just telling that it will even offset the hashing step. And well, of course, these strings were intentionally short so that they would not be dynamically allocated themselves. And just that extra step that you have something dynamically allocated somewhere actually offsets the benefit of hashing. So reading, and I tried to make the combination, like read element addressed in a flat map referred to by another element in a flat map. So basically going through, like in database language, you just look up a foreign key somewhere and then use the foreign key to look up something else. It went down to 10 million operations per second. And if you just do the things that are fast, iterating flat map, 800 million operations, iterating through vector, 2 billion operations, randomly accessing vector elements, 150 million. This one points out that you get more than 10 times higher speeds if you go linearly through the vector and don't access the elements at random. This is just purely the benefit of memory locality. And I have found that if you actually receive the index as a string, parse it to a number, because like it is a string, like, just write it out in a human readable form, and then you parse it into a number. And the result is that you can look up 30 million elements in a vector this way, which means that actually parsing the string to look it up in an element, parsing the string into an integer to look it up in an element in a vector is slower than simply looking up a string in this unordered flat map, which shows that, well, actually, even if you use this new C++17 stud from cars or to cars, it's still slower. It's still surprisingly slow, and actually hashing and using a hash map is still faster than actually parsing these numbers. Right. So, yeah. So the next part are the bottlenecks in parallelism. So a mutex can do 35 million locks unlocks per second. You need to keep in mind that stud mutex is a particularly efficient implementation. It doesn't do literally a mutex, like an operating system call. It has some optimizations, as like trying to first spin lock as an atomic to avoid actually suspending the thread and avoid a lot of other stuff. So stud mutex is fairly optimized, and still you get only 35 million unlocks per second, which pretty much, if you are just accessing a single container somewhere, you waste more, you spend more time locking and unlocking than actually making the lookup in that container. Stot atomic can do 130 million operations per second, so this one is still slower than, for example, if we look back, randomly accessing vector elements is still faster than using atomics, even though it is a huge vector of several megabytes where you will have cache misses and so on. So this is like quite, this shows that stot atomic is still can be a bottleneck, even though atomics are reportedly super fast. Yes, it is super fast compared to other approaches, but it is not so much faster than stot mutex. And it's also not yeah, and if you see that something is like a log-free data structure, it doesn't mean you just get free performance. If you just get several, if you need to actually do several atomics to access it, you pretty much just lose the advantage compared to just you doing the same operation, but by locking the mutex first. I was interested in trying some other approaches like stot shared mutex. However, stot shared mutex was slower than stot mutex. So even if you can make parallel reads, which are not exclusive with each other, and only writes have to be serialized and exclusive with reads, you are still slower than just locking and unlocking, locking it, unlocking, locking it, unlocking it. So stot shared mutex is useful only if you actually spend some more time inside this structure that you are changing, and it can be super convenient in some situations, but you cannot really use it to optimize your code. I was trying to implement copy on write using stot atomic. However, the problem here is that you cannot simply replace a pointer with another pointer, like just an atomic pointer, just replace it with another pointer, and it's now an updated version. The problem is that then you need to count the references so that they are located at the right time. At this point, I would think that if we really had a garbage collection that was written in the state-of-the-art kind, many of the parallelism problems would be solved by having a copy on write that would not suffer from the problems that you actually have to use additional atomics to find out how do you actually deallocate it, or maybe some other trickery if it is usable. If some tricks are possible in your context, but well, there are some, you see that this just, if you can avoid parallel synchronization primitives completely, you get some advantages, because you cannot really listen to the typical wisdoms that, yeah, this is log-free data structure, it's perfect, no contention. And also, if you have an atomic reference counter, you still need to increment it and decrement it after every read, and you can get a congestion on this read, which means additional problems. So you still cannot get like performance like if you didn't lock it. Yeah, this is all I have here. One thing that can bypass all of these problems are message queues, because you can actually shove multiple messages into the queue, and only after inserting a certain number of these messages, or inserting the messages for some time, you increment the atomic counter, how many of them are there, so that the reader of that queue can start reading them, which means that again it has a possibly fairly long batch of messages that it can respond to. This, of course, is super impractical without coroutines, or well, callbacks, but well, that one will be less practical. Of course, this is not the only way, but message queues are what they like the typical recommendation for this approach. However, after thinking about it for quite a while, I got some new ideas how else could this be done. And I have found that if you can afford some kind of latency, you are trying to maximize throughput, not response time. So of course, if you are doing HFT, this is not useful for in any way. If you are doing HFT, you need to structure it. Well, you still can use some parts of it, but this trick cannot be used. But the idea is you have a read phase where you just read and don't log absolutely anything. You can have as many concurrent reads as you want. You can have these things duplicated into individual CPU caches. There are no concurrency problems whatsoever because you are only reading. Then you just stop all of these threads. You make the changes you have queued up, and then you just come back to reading. Or alternatively, you can just, especially if the structure isn't too large, you can duplicate it and make this, and all of these changes that you are submitting are applied to this copy. And at some point, you stop these threads, you just swap everything for the copy. And then all of these requests that wanted a change will be unblocked because they, of course, have to continue after this update is done. And both of these ways can optimize the read heavily because you don't need to increment one single atomic counter that just counts the references. You don't need to read an atomic variable that contains the pointer. And that way you can get over this limit of stat atomic, which is around 130 million. You can get above it with the number of concurrent reads of the same structure. However, well, as you will see later, the atomics are still fairly fast, but first log-free data structures are still very difficult to get right, very buggy, and if you need multiple log-free, multiple atomic operations, which you usually need, then, well, you might start you might see some influences on performance. So next part, avoiding allocation. This is a very generic recommendation. Actually, I was forced into this at one point when some code was supposed to be usable also on embedded devices. And I needed to find ways how to just put everything on stack and then refer to it through functions and so on, and just keep it on stack to make sure that there are no that I don't fragment the memory, because in embedded environments they're always nervous about memory fragmentation because they have so little memory that you can just end up not having the right place for a bigger allocation. However, as I realized that, yeah, it should be useful for memory locality, and it was improving performance pretty nicely. And also I was making much less memory errors in that case, because usually the lifetimes were contextually defined, and well, I had to make some really serious screw up to get into some kind of memory error there. I'm not telling I didn't do it, but from this point, just if somebody started peddling Rust to me, I was looking like, come on, and it solves a problem that I face once per year. So yeah, this is both, it needs to think about it differently, but this is actually both practical and performant. Of course, this is opportunistic, but these are the usual things that work. Well, first thing is short string optimization. This now works for stud string since C++11. You don't even realize you are using it. Basically, if the string is small, 16 bytes long or shorter, it is actually within the stud string object, and you start dynamically allocating something only when it's larger. So unfortunately, I found that the main bottleneck with stud string is that these functions, for whatever reason, just don't like to inline. I don't know why. They just don't want to inline. And in many cases, I found that it's just better to make one vector of stud strings, and like if I needed a string-based lookup, I just put the stud string view into it so that it referred to strings from that vector, and it was so much faster just because I wasn't constructing stud string, which would be still pretty fast if it wasn't actually inlined, but it wasn't inlined. So be careful about this thing. I don't know why the compiler does it. Boost small vector. This is a neat trick. If you have a reasonable estimate what would be the maximum size of the vector, you can use boost small vector, which works so completely like stud vector, except that you have to specify the size. And that means that you can exceed the size, but only at that point it starts dynamically allocating anything. Next thing is stud variant. This is like the typical trick that you can, if you want to have multiple types, and instead of just dynamically allocating one of them, referring to that through some union or something, you just put all of these things into the same block of memory, and it's like a statically allocated object within whatever structure you have or on stack, but you just have a choice of multiple ones. There is this super useful thing for it called stud visit. So if you have some similar methods on these objects, then you can just actually write completely generic code for these different things that may be inside. Otherwise, even if there aren't, I found that using just if const expr is with some concepts does pretty much looks very normal, and actually you are doing some variant about on top of that. Stud function ref or boost function ref in case you don't have C++26. So you probably don't have any, you'll have to use boost function ref currently. This is basically like stud function, but it doesn't own the function. So if you are using a callback, but you are not going to bypass the, it's whatever is in the function you are calling is not going to outlive the context you are calling it from. You use function ref, and this way you avoid copying the lambda's closure or whatever else. Stud function itself will be fast if it is either just a function without the closure or the closure is smaller than 2 words. On a 64-bit architecture, this will be 16 bytes. Because in that case, and also you will need it to be trivially copyable, I think, because, well, of course, you don't want to have some non-trivial data structure there. And if you can take care of this, you avoid quite a lot of dynamic allocation here. Another thing is that the typical problem with C++ interfaces is that you usually dynamically allocate something, put it into a pointer to the interface, and then this way you achieve a lot of polymorphism. What you can actually do is that you instead put this object on stack and call a function on it that actually takes the reference to the interface. This way you pass it on, but avoid dynamically allocating anything. So this actually addresses most of the issues related to virtual functions. People were typically complaining like it's slow, but actually if you use this trick, it's not slow. And I was surprised how often can it inline these virtual functions. Another thing, if you actually allocate, it's better to just allocate everything to get, like, make a bigger object with all the stuff you need at that moment and allocate it once. If you are using asynchronous code, it's generally better to make a callback rather a coroutine over a callback, because if you are using a callback, the disadvantage of the callback is that you especially if you are using something like Boost SEO, you create a callback, then you queue another callback as a response to whatever asynchronous call you are doing. Then you queue another callback, and so on. Each of them is dynamically allocated, again, copying most of the contents into the new callback. This is fairly convenient to do in with lambdas, but at the same time, it's basically for every resume or like every suspend, you need to dynamically allocate the new object. If you use a coroutine, you still need to dynamically allocate it, but you just allocate it once. And you just resume it at another point and at another point and another point, but you are not copying anything, you are not dynamically allocating anything again. You're just using the same coroutine object and returning to it multiple times. Okay, this is an example of the part about the, well, one specific case that I was seeing very often is that you are parsing JSON. Usually, most of the libraries for parsing JSON will build a data structure of that represents JSON, and then you just traverse this data structure and find whatever you need there. Some of them that are fast will do things like we have a custom allocator optimized for our use case, which is generally fine, but which is better than nothing. But first thing, I don't have so much faith in custom allocators because malloc is nowadays very good. And another thing is that you still have these objects scattered across memory. They were parsed in some order. They were put into these whatever structures these custom allocators build. They were put there linearly. I have found that the same thing can be done with some kind of callback or interface, something in between, where basically you just supply to the parser what it should do with different values that it finds. This is just something I came up as an example quite quickly. I actually had it implemented before, but I wanted to replace it in this thing. But first it was more complicated, and I experienced that I ended up not doing that. I think I forgot, but the idea is the parser just gets an implementation to this interface, and you are typically just translating the JSON into whatever data structure you have yourself, where you actually need the data. And you can just make a callback to it. Well, not exactly callback because it has multiple methods, but the idea is it's searching through it, finds a string, so it calls on string. Finds a number, it calls on number. If it finds a bool, it calls on bool. If it finds a sub-object, so like just another JSON object, then it calls a callback that will provide it another instance of the interface because it's now parsing some different object. If you want an example of this actually implemented, not just an example how this could look like, I can show that to you. I have written it in the past, and I was surprised how fast it was, because it was basically just streaming the data as it came without needing to first build a structure and then actually read the structure back. Next part is SIMD for string operations. There are way too many binary protocols that are, well, binary protocols are obviously faster, but in practice, you'll just find so many text-based protocols everywhere, which very often have the problem that you need to find a delimiter. So basically, if you want to parse it as fast as possible, because just HTTP, JSON, XML, and so on are things that you need to process quickly. One of the typical approach is that you create some kind of, well, if you are slow, well, it can still be pretty fast with that, but if you want to make it even faster, you can use SIMD. SIMD, the typical example using, well, simultaneous. Well, you could just tell what is shortcut, single instruction, multiple data. So you can use these special instructions. The typical examples that you will see is that you are computing some kind of 3D graphics and you have a vector like of coordinates and you need to do some vector multiplications. You create some matrices. Maybe you can do some matrix multiplications there, additional vector string vector normalization and so on. Those are the examples you usually see. But these instructions work also in different sizes, including 1 byte sizes. In that case, you get 32 characters and you make operations on all of them with a single instruction. So currently it's available only as experimental, but it's part of, and it was standardized in C++26 with very little changes. I think some important bits were omitted for whatever reasons. But especially there was one situation where the CPU instruction did exactly what it was supposed to do, what it was convenient if it did, but it was in that corner case declared that it is undefined behavior. Yeah. It can, well, you need to handle that case, but because you will do this operation on all of these 32 characters.
Bytes which don't use the instruction. It means additional allocation in most cases.
No, you don't allocate anything. You just put it on stack.
So it will be just access of stack or flow, right?
No, I mean, what do you mean with additional allocation? Because
I mean, I need something into the scene.
Yeah. When you are creating this object, there is some function for that, and there are multiple. Well, you also need this data to be aligned to be actually usable as SIMD string. So you need to copy it from whatever origin it is into the SIMD structure. So because the SIMD instruction needs to be aligned so that it would be usable for these AVX instructions. It needs.
So it's just string aligned.
Yes, but in practice, if you are parsing something, it will definitely not be guaranteed to be aligned. So in that case, you already need to copy it, and when you are already copying it, you can just copy less bytes. You are using memcopy anyway.
I'm trying to say that even copy already can consume it, and you could just create, for example, your JSON parser. It means that, you know, for me it will be necessary. Okay, I will do it on the fly, but then I need to copy something, and only after that I will try to use this data.
Yes, the problem is that you need to copy it once, but the copy is much faster than iterating byte by byte.
It's really cool statement, because everything which we already just read will be in cache.
Yeah, that's true. We basically you have it in cache, but the main problem is that, yeah, but you are the bottleneck will be the instruction bottleneck if you are going byte by byte, because yes, you cache it everything, but you need to go instruction by instruction to check every single byte if there is the delimiter. You are searching for, yeah.
Comparison will be not byte after byte, right?
Yes.
So currently I see this bottleneck I need to align, but I don't see bottleneck in comparison to string views.
Yes, if you are comparing string views, again, you are looking for a difference at some point.
That's right.
And this is the bottleneck you are trying to avoid, because you can copy many bytes at the same. If you do something like memcopy, it is actually super fast because it's using some 16-byte copy instructions. And as a result of that, it's very fast.
Just to clarify, from my observations, when I measure something, it really depends on cache size. Really.
Yeah, cache is important, but you get another bottleneck if you are searching through a string byte by byte.
Yes. String.
So this is the trick how to avoid looking for some character byte by byte, because in that case you need to do 32 iterations. In this case, you just do a bunch.
I just cannot for the statement one more thing.
Yep.
If we are reading even byte after byte, processor usually predict what we are going to read next, and it will be extremely fast as well.
Yes, but in practice, if it predicts what you are going to read, well, it typically just downloads a bunch of data all around it, so you get just, I don't know, 2 kilobytes. No, probably not, but you just get much more bytes than 32 bytes if you are just reading it. Yes. However, well, that way you just, well, because there are multiple levels of cache, you're still, I'm not, well, we are not, I don't know about which specific cache we are talking about, if it is L1, L2 or so on. So you will definitely, L1 cache is just 4 kilobytes or something like that, maybe more. Yeah, I just don't remember what's exactly this number, but you probably have multiple groups of data you were accessing recently there. So you probably get, I don't know how much exactly memory of this data you get, but it's definitely more than 32 bytes. So this problem with the memory availability, that will not be an issue. The issue is that, well, this one is already optimized by the CPU, but another bottleneck is just going instruction by instruction and looking for it. Yes, the CPU can use some, like, just if it sees this kind of pattern, it will assume use this kind of speculative execution quite reasonably, but yeah.
Say that it's not really precisely for everything.
Well, no, it's practically for every case, because pretty much in every situation you already have it cached when you are actually searching for it. This one gives the additional. This one addresses a new problem that you can still face, and that is that, well, you still can have speculative parallelism within that it tries to predict the branches in the searching for some kind of character. Yeah.
Usually I perform strings in my applications, online.
Yeah.
If I would solve some kind of vocabulary issues, I would definitely allocate and try to use CMD. At the same time, if you're talking about parsing of JSON, I would avoid this because it's just online processing and it's flag processing. I wouldn't put any copy in the.
Well, in practice, it depends on which level you are talking about, because you are explicit in C++, you are explicitly writing that you are copying into the SIMD structure. You make a few operations, you get some result out of that. But in assembly, you need to understand that you are actually managing the how is it called, the registers, and SIMD has its own register. So you are not necessarily actually copying it into a different area of memory. You are just loading in it to a register so that you could work with it. And if you're using SIMD, you have a SIMD register, and you just load these 32 bytes into the register, and you are not copying the data at all. Well, you are still copying it into the register, but you would have to be copying into the register either way. Actually, I forgot what I saw in that assembly when I was looking at it. Well, looking for delimiters is a very It's like a very low-hanging fruit, obvious use case, because, well, actually have it as an example right after this, so we'll get there. So there is this fixed size SIMD where this is 32 byte large. Well, if the byte size is 32, then this one is 32 bytes large, and it contains, and like in memory, it is just lines, basically the same as an align stud array, but operations that you are doing on it are overloaded in a special way so that it behaves like pretty much if you were just editing a single, you write the code as if you were editing a single element, but actually it modifies all of them. So if you have an object like this, which I found to be pretty convenient for many things, so if you have a method that is supposed to find some letter in the string, you create a fixed size SIMD mask, which, well, if you have a 32 byte character, this would be a 32-bit integer, and you just compare the element bytes with the one letter that you are looking for. So this looks like fairly normal code, like if we were working with a single character, but this is the great overload of this new addition to C++. And if you compare it, you get a result that's an integer where every bit indicates if the corresponding byte on that index was the same as the letter, as the character we are comparing it to. This way, you just get an integer where every bit is the result of comparison of the corresponding byte. So there is this method std_none of. So you compare it with the letter that, well, yeah, you find if none of them is there, so you haven't found it in that case, and you have this find first set to find the first bit that is 1. There are similar methods like find last set, find first not set, or something like that.
The result would be bit mask?
Yes.
And we are talking about bit operations, where we are talking about
well, these basically do the typical bit operations already. So you get the found is the bit mask, and these are already bit operations, because you do only one SIMD operation in this whole thing to find the method.
The exact result of SIMD operation if we want to call. At the same time, when we are talking about next line, it will be search of the bit inside of the set 2 bits, right?
It will search for what?
For one bit. Find first set.
Yeah. Yeah, find first set will give you the first bit that is 1. Yeah, the index of that bit.
Better than linear.
It doesn't do it. It doesn't do it. There is a single instruction for that.
In SIMD.
No, this is not the SIMD instruction. Just the found is a 32-bit variable.
We are talking about one single instruction, std_none of.
Yes.
One instruction.
Yes.
And then std find first set, it's also one instruction.
Yes. You are not looping through the bits of that. Yeah. Well, this is basically a 32-bit integer. This is comparing it to 0, basically the same, just you need to use different, well, you could probably, well, you totally can just reinterpret cast it to 32-bit integer and then just compare it to 0 and then use, in C++20, there was this this new header called bit, and you can actually, yeah.
At the same time, why not size t?
Where size t? Yeah, you mean the result?
It was more obvious because it was signed.
Yeah, the reason why I'm using signed is that there is a, well, I found that unsigned is a super good source of mistakes. There was actually some article from Herb Sutter and Björn Strostrup recommending to try to avoid unsigned for anything accept bit operations because it's error prone. No, well, this is the resulting value is an index, which byte is up. So that is not a bit operation. The found, if we cast it to an integer, we would have to use unsigned integer because otherwise it would be very error prone. But the result is an index. It's not used for bit operations anymore. But you know, I don't want to argue about code styles. I guess if you don't like it, then you can do it yourself. There, it's not necessary. Okay. So yeah, actually, I have told this one already. Yeah, it can get quite tricky. For example, if you want to 0 bytes after a certain index, then there is actually fixed size. No, the stud.simd actually has some operation for like perform these operations on the elements where the mask is 1, but it just kept constantly emitting assembly code that just iterated over 32 elements, which turned out to be a huge performance bottleneck. So I needed some more algebraic trickery to find out how to actually do some of these operations. One thing that I wanted to do is that, okay, I have found this, I have found the delimiter, and now I would like to get out the string that actually ends at that actually has zeros after from the delimiter and everything after, so that I could use it as an identifier somewhere and so on, and just use again SIMD for comparisons. Because I have parsed out like the name of some element from the stream, and now I want to blank the other bytes afterwards, so that A would be equal to A even if and so that I wouldn't have garbage after this first byte. So to deal with this, I have found that well, one thing I can do is to, well, the thing that should work in theory is that I get a byte that is well, I found the first one that is set, which is the delimiter, so I want to shrink it to the size given by the delimiter. So I can do some bit shifts on the integer to create a bit mask that contains ones and that contains 0, 0, 0, and then 1 from the delimiter and everything afterwards. And then I assign 0 to all elements after it. However, I found that this is not so easy because it just kept emitting 32 iterations. And what I found that I could do is that I create a context per variable that I manually set to numbers 0, 1, 2, 3, 4, 5, 6, 7. Then I subtract these. So this is a constant. This is a mask that, wait, no. This is the result that this is a temporary variable that I'm using. So I subtract all the, how is it? Yeah, I subtract these 1, 2, 3, 4 numbers yeah, I subtract the new size that I want so that the numbers are negative before the place where I want to change it and positive afterwards. Then I use these bit operations to just keep the highest bit so that the bytes where it was lower than 0 will be 1. The bytes where it was, well, will be like the first bit will be 1. And the bytes that were after the delimiter that I want to blank, then it will be 0 in the then it will be 0 in all bytes. Then I do a bit shift by 7, which will replace those bits that the part that I want to keep with just full ones, and the ones that I don't want to keep with just zeros. And then I do a bit end, which means that I zero all the bytes after the delimiter, and I just get the part of the string I'm interested in. So it took me a few hours to figure out this trick.
Prefabricated array of 30 masks and then just get used by index and
Well, that would be definitely easier. But I'm not sure what would be the result of performance, because it would actually create quite a lot of constants, and the instruction cache might get overloaded easier. But on the other hand, I would have less instructions here. So maybe that one would be, I wonder what would be that, how would that affect performance? I didn't think of that actually.
Yeah, I didn't quite follow. What does the subtraction of an integer from a fixed size thing?
Which one do you mean? Yeah,
Yeah.
the bytes that were below 0, well, I subtracted, and the ones that I want to keep will be negative, and the ones that I don't want to keep will be positive numbers.
So it subtracts this integer from every element of the string, right?
Yes. Okay, one thing is state machines. We all don't like state machines for parsing, because this always creates very long functions with a lot of long switch cases, and it's super ugly. However, if we use something like regex, it will be just so slow. And if you just write a normal function, you basically have to abort the parsing if you run out of bytes that you are reading from the stream. So if you are writing just a normal function, so it's, well, you may want to actually abort the parsing and retry again once you get more bytes. But if you use a state machine, you can just interrupt at any moment, just like in a coroutine. But the coroutine will mean another dynamic allocation. So this thing can give you a little bit of performance. There are some advantages, but it's just a bit of optimization if you see that there is, like, your parsing code is still taking longer, maybe that you think it could be shorter. So this is one thing that works. What I have, well, I'll mention something about it later, but in general, if you just hand roll the parser, it will be definitely faster than using some regex or something like that, unless you have a compile time regex. So minor optimization, well, just obviously, if you just open it in a profiler and you can find just which parts are hard. One thing that I found strange is, especially in case of SIMD code, they are not being inlined for no obvious reasons. If I put force inline there, it just became faster. And well, obviously it was also inlined, but it became fast. It just became faster. I don't know why the compiler wasn't marking it as such. However, I found that it's best if I just benchmark it after trying to add this force inline for every single line that I was, every single function that I would have preferred inlined, because I found that in one case, for whatever reason, it became slower if I inlined it, but it became significantly faster for most of them. So just basically one force inline, rebenchmark, one force inline, rebenchmark. So, and another thing is, sometimes the function just takes more time. You just try to reformulate it somehow, it will be faster. Just if you see something is a clear bottleneck, sometimes just trying out helps. One thing that I found really bizarre, and I think it hints on some pretty strange corporate practices, is that usually they tell you use microarchitecture native so that you get the most performance because we optimized for your CPU. I have AMD Zen 5 architecture, and I put their architecture Meteor Lake, and it was 10% faster. I think that Intel was seriously trying to compensate for having worse CPUs by improving compilers and locking these improvements under optimizations for their microarchitecture. I don't know what other explanation for this exists. But I just, whatever, mark your AMD CPU as Meteor Lake and it's faster. So at this point, well, testing with actual networking would be insane because I was pretty sure that the performance of any hardware I had wasn't sufficient for this. So I have created a system that first generates a request, an HTTP request, takes some, and then it is parsed through SIMD. There is a typo here. I was using a fixed size SIMD string as a string for identifying elements in tables, so that I would get some performance boost from having quick strings. Then I would either respond with a prepared static value, which would be like just, okay, in the case we are just getting some static resources. Actually, it was changeable. It wasn't hard-coded, but the point was that I didn't mean to change it over the run, or just look into a string index table of boost unordered flat map. I was queuing write operations and executing them during these special phases that I've described that were running every 100 milliseconds. It turned out that actually these switches that I had to do 10 times per second actually took 2% of the total time. So if I wanted to optimize it more for latency, I could do 10 milliseconds, and it would spend 20% of total time, which could still be acceptable in this approach. So as long as you are not doing HFT, this is totally a doable optimization to get a massive number of concurrent reads. I was actually setting these things that 50% requests get the static resource, 25% get another static resource, then 1.6 set a value, 1.6% delete a value, and 21.8 gets a value from a table. From what I know, when I was looking at some benchmarks for web servers, this is quite a huge number. This like unrealistically large percentage for things that actually modify stuff. Okay, so first I was comparing it to something, so I wanted to know how many users would that be. So I have just measured myself doom scrolling Reddit and found that I was emitting 2 requests per second to Reddit, and but I have found that for benchmarking, like testing if a website has enough performance, the assumption is like can be even 10 requests per second. So now like after all these optimizations, I was able to respond to 100 million requests per second with my powerful machine. So, okay, so I don't know how many CPU cores there, but it's still one, nothing distributed, just one server. How many? Just like, okay, that's quite a lot of concurrent users that could be there. So I was just looking at, just out of curiosity, after seeing an advert somewhere. So I was looking for adverts like this. So what we're explaining how to just do these modern web designs. Even Google Gemini agreed on that. Even the random Indian YouTuber agreed on that. So I have summarized it with this meme. This meme is not super fresh, but okay, I guess. yeah, before I get to that, I lied a little bit with describing my server that I don't have. I was just running it on this laptop. So I assume that if I had actually a serious server, it would be a wholly different number. So, yeah, okay, so bypassing OS sockets. So the one thing that I missed out because I wasn't able to practically test it was actually doing the networking quickly. Because if you look at out, a small HTTP request can be 100 bytes large. If you have 100 millions of them, you get pretty close to 100 gigabits per second, which is, well, there. I just did a quick Google. I found there are some network cards for that. Typically, you'll find some from Broadcom or NVIDIA Mellanox. And they even use some optic cables because you cannot do it with RG45 Ethernet, but these are pretty real. These are normal things that exist. And but however, the problem is that if you are on a local host and you have 32 kilobyte packet size, this is pretty normal. However, in practice, you will find that TCP packets will have around this number of size. And doing a syscall for every packet, this would be, well, quite a problem because the kernel will need to do some internal locking again. I just not get that performance. So in practice, what exists is that these more powerful network cards will have some possibilities, like probably some kind of specialized hardware for doing this, that they get TCP packets, or maybe just any packets. They check the sender and the port of the sender, and probably also the receiver port. Oh no, this is actually configurable, which part should be included into that. It computes a hash and it splits it into some number of buffers, and it will write it to the corresponding buffer, so that if there is a communication between one client and his port with the server and one specific port, it will always go into the same buffer, so that each connection goes into the same buffer. I think it can be configured also that everything from a certain IP address will go into the same buffer. And these buffers are in the main memory. They go straight into RAM. They are not going through the CPU. This means that the idea is you just you get access to this in user space, and you just see a buffer, and the network card is directly writing packets into this buffer, and each CPU has its own buffer of requests that it is processing, and it is its own connections that belong to it, not to other CPUs. So this way, you don't need to actually do any CPU interrupts for packets. You don't need to actually decide into which buffers it needs to go and make sure that you don't lock and don't override it because you threw the interrupt into the incorrect CPU and so on. This means that you don't have per packet interrupts and syscalls, but of course you need plenty of syscalls to set this up and probably to send some notifications about buffers being full or stuff like that. But if you don't do it per packet, if you do it per, I don't know, 100 packets, it's still a massive improvement. Once again.
Are we talking about writing drivers for the card?
Not about writing drivers for the card, but because these drivers, I'm explaining how these drivers work. I'm not telling that you are gonna write it.
No, I'm just trying.
Yes.
This data came, right? But there's this data anyway to the card itself. So I need to get the information I read on process.
Yes, all of this basically has to be done on the driver level so that your user space application can access these things that it receives. But of course, this needs to be, the things that I'm describing now is done by a driver.
Oh.
Yeah, I'm explaining how this, how can, what is the alternative to using operating system sockets?
Yeah.
Not just how do you implement it. Of course, I wouldn't be implementing this thing myself. So, as I just said, this requires special drivers. This started being provided by a data plane development kit, which started in 2010 or something like that. It was didn't integrate well into things. It was quite hacky at places, difficult to set up, and so on. But it was at the same time very useful. And eventually, there came to be a new kernel API for this. It's called Express Data Path. This thing is much better. Well, it's not better. It's actually is well integrated into kernel. The kernel takes care of this, solves all the major hurdles, gives you proper, doesn't allow you to like a random application to spy on whatever traffic is there. Although before I found about this, I was finding that you can use so-called raw sockets to just listen to everything and then just throw it into a buffer that you provide yourself, which means that you can bypass the kernel even that way. But then I found that actually I was discussing this with somebody, and he suggested me that it sounds like this DPDK. So I started looking into that and found that somebody has done it already and has done it much better. So, and now there is even this kernel API XDP. This XDP does an extra thing that to make that it actually filters the packets a little by having a possibility to write some kind of program that the kernel compiles and filters these packets so that they can be prepared before they actually get to user space, so that you avoid reading some unrelated communication. The consequence of this is that it's slightly slower than DPDK, but from what I have read, better integrated in an operating system, easier to set up, and has plenty of other advantages. So, of course, the problem is, does it implement the TCP logic? Well, no. If you are trying to use it to get just as much performance as possible from your UDP application that just avoids all the higher level logic for maximum output, this is where you probably may want to go. However, implementing TCP doesn't sound like fun, given that there are all these kind of TCP replication attacks and different abuses of delaying responses and just using DDoS in smart ways than just sending too much stuff. So this is not so. Again, I found that there is a library for this that does this pretty well. It's called s.r.o. It's written in modern C++. Coroutines, you have plenty of functionality to get all this low-level networking done. It can work both with DPDK and XDP, and even Unix sockets if you are just testing something. The disadvantage is that it's Linux only, and its CMake, as I have found, is so obsolete that while I was trying to get to using it, I had enough material to give a talk one month earlier. So I can give you some the CMake. If you want, I can give you the CMake I created that will install it. There is plenty of workarounds, but at least it works. But yeah, maybe I forgot to mention, DPDK is Linux only. XDP used to be Linux only, but now it is provided also by Windows. But s.r.o is Linux only still. Using s.r.o for basic networking is surprisingly simple. I found it actually easier to figure out than Boost SEO. Basically, if you just want to make, I just wrote a server that does welcome, that sends a message welcome, then waits for a response, and then just responds it back, and it's just the short code and does it very fast. So it's not difficult to use given how deep low level you go with that, thanks to modern C++ being actually finally modern. Actually, it has a lot of other functionality. So it has its own scheduler because, well, there are coroutines. So basically you need to do your own scheduling. It does the scheduling in ways that are kind of optimized for the purpose that, for example, it may poll for incoming packets so that you don't get any interrupts if you are busy, but it can actually start sleeping in case there are no packets for some time so that it doesn't just poll endlessly. You have also the networking client and DNS resolution so that you can also work as a client, not just server. The same asynchronous reading and writing also applies to file systems. So you can get the asynchronous access to files as well to get it faster. There is it comes with its own allocator, which takes advantage of breaking the execution into some single-threaded shards, which communicate with each other through message queues, which is another thing that it again implements. These message queues, as I mentioned, they are very useful, and the main way how you can avoid most of the inefficient synchronization there is that you just make queues between every two CPUs or hardware threads. And if you have a lot of messages, you actually increment an atomic number that, yes, now you have new batch. So this is probably implemented in the scheduler that if there is a timeout that they're not sent for some time, it's just flushed again and so on. So this is in this way quite optimized. You can have task scheduling groups so that you decide how much of the overall time individual groups of tasks get. It has its own HTTP parsing. And I have found that it's using some tricky thing that you can just declare some library where you just declaratively do something, declare what you are going to parse, and just does some kind of code generation stuff that creates a state machine that will compile it, and you avoid all the ugly parts. But as I have found, there is no SIMD. Well, actually, I was even surprised that it's not just some kind of Lua. It's actually not bytecode. It's seriously compiled into the code and everything. And it also has some debugging utilities. I found that in debug mode, it was giving me warnings about memory leaks and other stuff. So when I was using it incorrectly, it was alerting me because of some sanitizers. I'm not sure how did this exactly work, but it definitely was linking Valgrind into it. This is basically a complete solution for doing a lot of high performance, low level stuff. And the main reason, well, it was not developed as just a standalone, it is a standalone library, but it wasn't just developed with the idea that, okay, let's just do one thing. This was created for some very fast recent database called SkillaDB. And they have created this as some kind of framework that is usable alone, but it was mainly meant for the database system so that they could get their database faster than everybody else. Yeah, and that's the end. So, oh, one thing I wanted to explore it further, but well, I was bogged down by this fight with the CMake, and I started preparing it. I found that I have played around with it, experimented with it, but I didn't build like just translate the original code I have for C-star because there are many changes, and I would like to do that, but well, didn't have time for that, and also I got sick recently, so I couldn't. So I failed to do a few things. So here is the conclusion. In common networking setups, pretty much every step tends to be implemented quite suboptimally and with significantly lower performance, even if the code looks like, yeah, there is no obvious delay, but in practice, everything can be done faster if you look at it. Even if you, for example, if you look at Boost Beast, you put there like parse HTTP header, it returns you a structure that contains plenty of stat strings from there. But come on, stat string, you're doing so many allocations there. So there are just these typical comparisons, like people often use a database instead of C++ containers for stuff. I know the database gives you the persistence. With a container, you would need to deal with it, but the performance difference is huge. And in case of, and people usually don't do some complex queries that's, well, so many use cases, you don't seriously need a database. People just use it and see it as a synchronization primitive between threads. That's definitely, well, it works, but you create a performance bad bottleneck. Another thing is about locks, which often make things slower or may become the bottleneck. Especially the more CPU cores you have, the more bogged down it becomes on individual locks. Structures, custom. Frequently, I see various libraries with custom allocators. Well, I could imagine how their APIs could be designed without actually allocating anything. One example of this is SIMD.json that I have found somewhere. It's a JSON library capable of parsing 3 gigabytes of JSON data per second on single core. But when I was looking at it, it was super easy to use, easy to figure out how to use it. But they were speaking how super fast is their allocator. But I could still see, yeah, I build this structure and then again I put it into the objects that I'm using in my application. Doesn't make any sense. I could just put a callback and just load it into my structure as it is parsed, and it could be even faster. So next thing, byte by byte parsing versus SIMD. This is again the part that the SIMD.json addressed and got this speed of 3 gigabytes per second. Actually, I was experimenting with it myself and created a JSON parser that was avoiding allocation. I got to 1 gigabyte per second. So apparently SIMD matters more than avoiding dynamic allocation. Another thing is regex versus explicit state machine. Regex just won't be fast. If you want to be fast, don't use it for parsing anything. And well, it's just using Unix sockets or Windows sockets can be limiting to your performance. But of course, if you don't use a special network card, it doesn't matter. And if you are just testing something, Unix sockets are actually completely fine, because if you use localhost, you can have 32 kilobyte buffers, 32 kilobyte packets. And when I was measuring it with C-star, I could get to 300,000 small packets per thread per second. But if I made them 32 kilobytes large, then I got to, well, the speed went down, but it was possible to get within this laptop several hundred gigabits per second. So you might have if you have an application that can actually work with the data that comes out from a really high performance networking card, localhost can deal with that load still, even with Unix sockets. Okay, that is, I think, all that I wanted to say. Thank you. Any questions? Any questions? Mm-hmm.
What happens when you want to add persistence to your database?
Well, you will be probably limited by the, well, of course, it depends on the strategy you are doing, because how do you persist? You can, wait, accidentally I made a quote from Agent Smith in Matrix, but that didn't mean that. But if you want to save data into the database, well, into some file, you can, well, one option is that you serialize it periodically, which means that if it is really huge, it's not very practical. If it is reasonably large, you can just, well, you may, for example, pause the program or copy it, or well, in other situation, you would need to use some kind of lock, depends on the way how you did deal with it, but you still are trying to parallelize this, but usually it's a matter of serialization. And it really depends on what you are, how you are doing. If you are just doing it periodically, it's simple. And if you, for example, already have copy on write, then you can just periodically write some kind of version. And when you are shutting down, you shut it down, and then you update it. For if you want to, well, the typical safety is that you create a new file, then you delete the old file, then rename the new file so that you always have the data on disk. This is the simple way. What is done in practice is that if you make a change, you put it into the journal, which is a file where you just write it every change that you do. You just list the changes there, and you can do this very fast. And you, for example, every coroutine that actually suspends on the write, it returns from the write after the write first is done to the part that is in memory, then it goes to the journal, which is just another phase, which may be done through another CPU. And then you just write it, and then the coroutine resumes that, okay, I have successfully written it. So, which means there is longer latency, but you get it confirmed that it is already in the journal. And if you are writing this journal, well, if you just resume from a crash or some kind of hard shutdown, you read the original file, you read the journal, apply the changes again. If you from time to time, you just create a new file with the changes already done and delete the journal. And I think another option is that you write it into the journal, then you confirm it, and then you already update the file, which, however, means that you will have some fragmentation issues, but that's how SQLite does it.
So basically, with some trade-offs,
yeah,
regarding the time over which you guarantee consistency, you preserve most of the performance of the purely run implementation.
But when I was looking at typical speeds of databases, when it comes to writes, these get to 20,000, I think, like 20,000 per second per database. So usually this is solved in a larger system by like sharding it again, and then just merging it so that you have constantly some inconsistencies, but You just have some complicated algorithms to ensure that it ends up being saved wherever you want. If you keep it in memory, actually, in the example I was showing, it was doing the number of operations, the modifying operations that it could do. Among the other things during the write phases was larger by an order of magnitude than the performance that I have seen. So you already get a massive performance boost from keeping it in memory, and you basically only add latency if you use the journal to ensure that it is actually real, because it doesn't affect your output. Anything else?
I mean, where to apply resume, I do have any.
Well, I was working in pure storage, seeing bits of it, but much of these were my own experiments, which I was preparing and just checking out stuff, how it works, benchmarking stuff, optimizing, figuring things out. But well, I worked in pure storage. Now I'm working at Broadcom. We do see these things.
Broadcom?
Yes. Yeah. Anything else?
Yes, yeah. Write something like this for myself. Never in practical use.
Well, and did you figure out the same tricks?
I would say that